That dim, fuzzy smudge barely visible in the night sky is hiding something from you, something so profoundly disturbing about the nature of space and time that your brain will struggle to accept it's real. This is Andromeda, and its distance will terrify you. And here is a question. If you could break one law of physics for a day, which would it be, and what would you do? Share your wildest idea in the comments. I will pin the most creative answer. Now let's begin. The Andromeda Galaxy sits 2.537 million light-years away from Earth. Let me put that in perspective. A light-year is the distance light travels in 1 year, moving at roughly 670 million miles per hour. At that speed, you could circle Earth's equator more than 7 times in a single second. Light is the fastest thing in existence, the cosmic speed limit. Nothing in our universe can move faster. And yet, even at this incomprehensible velocity, it takes 2.5 million years for light to bridge the gap between Andromeda and us. Think about that for a moment. When the light you see from Andromeda tonight first began its journey, there were no cities on Earth, no pyramids, no written language. Our species, Homo sapiens, didn't even exist yet. Our evolutionary cousins, Homo habilis, were crafting the first stone tools in East Africa. Saber-toothed cats prowled the continents. Mammoths thundered across Ice Age landscapes. And all that time, while civilizations rose and fell on Earth, while our species emerged and spread across the planet, while we invented agriculture, built monuments, sailed oceans, and eventually reached for the stars themselves, photons of light were silently racing through the void toward us. We measure Andromeda's distance using some of the most clever techniques ever devised by human minds. Astronomers don't have a cosmic tape measure. They can't bounce lasers off distant galaxies like surveyors measuring a plot of land. Instead, they use what scientists call standard candles, celestial objects with known brightness. One of the most reliable standard candles is a special type of star called a Cepheid variable. These stars pulse with remarkable regularity, brightening and dimming in predictable patterns. Here's the brilliant part. The rate at which a Cepheid pulses tells us its true brightness. By comparing that true brightness with how dim it appears from Earth, we can calculate exactly how far away it is. It's like knowing the wattage of a light bulb and using how faint it looks to figure out how far down a dark road it sits. The Hubble Space Telescope revolutionized our understanding of Andromeda's distance. Launched in 1990, Hubble gave us eyes above Earth's blurring atmosphere. It identified individual Cepheid variables in Andromeda, stars pulsing away in a galaxy so distant they appear impossibly faint. By studying these cosmic metronomes, astronomers refined their measurements. More recently, scientists have used eclipsing binary stars, pairs of stars that orbit each other and periodically block each other's light. By carefully analyzing the dimming patterns and measuring the stars' actual sizes and masses, researchers determined Andromeda's distance with stunning precision, 754,000 parsecs, or about 750,000 light-years with an uncertainty of just 4%. In 2026, we're more confident than ever about this measurement. But here's something that should genuinely terrify you in the most wonderful way. Andromeda isn't staying put. While most galaxies in the universe are rushing away from us, carried along by the expansion of space itself, Andromeda is doing something different. It's coming straight at us. Right now, at this very second, Andromeda is hurtling toward the Milky Way at roughly 70 miles per second. That's about 250,000 miles per hour. To put that in human terms, if you could drive a car at that speed, you'd circle Earth in less than 6 minutes. Now, before you panic, let me reassure you, this isn't happening tomorrow. The collision, if it happens, won't occur for roughly 4 to 5 billion years. But here's where it gets genuinely fascinating. For decades, astronomers assumed this collision was inevitable. They ran computer simulations showing our two spiral galaxies performing a cosmic dance, swinging past each other, gravitationally disrupting each other's elegant spiral arms, then eventually merging into a single, massive elliptical galaxy that some scientists playfully nicknamed Milkomeda. However, recent research published in 2025 in Nature Astronomy threw a fascinating wrench into this story. Using the most precise measurements ever obtained from the Gaia and Hubble space telescopes, astronomers realized something remarkable. We're not as certain as we thought. The study found that when you account for all the gravitational players in our local group of galaxies, particularly the Large Magellanic Cloud and the Triangulum Galaxy, also known as M33, the outcome becomes far less predictable. The Large Magellanic Cloud, a small galaxy currently orbiting the Milky Way, moves on a path that runs perpendicular to the Milky Way Andromeda orbit. Its gravity tugs on both large galaxies in ways that actually make a collision less likely. Meanwhile, M33 increases the probability of merger. When scientists ran thousands of simulations incorporating all these factors, plus the uncertainties in each galaxy's exact position, motion, and mass, they discovered something stunning. There's roughly a 50% chance that Andromeda and the Milky Way will never collide at all during the next 10 billion years. Think about the humility that requires. We've studied these galaxies for generations. We've built space telescopes, developed sophisticated physics, created supercomputer simulations, and yet despite all our knowledge, we still can't say for certain what will happen to our own galactic home. The universe keeps reminding us how much we have yet to learn. Let's talk about what 2.5 million light-years actually means in practical terms. Imagine you're an astronaut with access to the most powerful rocket engine ever conceived. NASA's Parker Solar Probe, the fastest human-made object ever built, reached speeds of approximately 430,000 miles per hour when it dove close to the Sun. At that breakneck pace, crossing the entire width of Earth would take about 3.5 minutes. Sounds fast, right? Now let's point that probe toward Andromeda. At that speed, the journey would take roughly 3,700,000,000 years. That's almost as long as life has existed on Earth. Bacteria would have time to evolve into fish, then amphibians, then reptiles, then mammals, and eventually humans, all while you were still in transit. But let's be even more ambitious. Let's imagine you could travel at the speed of light itself, breaking every known law of physics in the process. You'd still be in for a 2.5 million year journey. If you left Earth today traveling at light speed, you wouldn't arrive at Andromeda until the year 2,526,026 AD. By then, assuming humanity still exists, we would be so changed, so evolved, so utterly different that we'd be unrecognizable. This is the scale we're dealing with. This is what astronomers mean when they talk about the vast cosmic distances. And Andromeda, despite being impossibly far away by human standards, is actually our closest large galactic neighbor. It's right next door in cosmic terms. The Andromeda Galaxy itself is a marvel that deserves our attention. It contains approximately 1 trillion stars. Let me say that again. 1 trillion, that's 1,000 billion. If you counted one star per second, never sleeping, never stopping, it would take you 31,688 years just to count them all. Each of those stars is a sun, potentially with its own family of planets. Some of those planets might harbor life. Some might host civilizations asking the same questions we're asking right now, looking back toward the Milky Way, wondering if they're alone. Andromeda stretches about 220,000 light-years across, making it roughly twice the diameter of our own Milky Way. When you look at Andromeda through a telescope, you're seeing it tilted at an angle, like a dinner plate held at a slant. If you could see the full glory of Andromeda with your naked eyes, if your eyes were sensitive enough to capture all its light, it would appear 6 times wider than the full moon in our sky. The only reason we see it as a faint smudge is because its light is spread across such a large area that it's too dim for our eyes to register properly. At the heart of Andromeda lurks a monster. Like most large galaxies, Andromeda harbors a supermassive black hole at its core, but Andromeda's central black hole isn't just big, it's enormous. It weighs in at roughly 100 million times the mass of our Sun. That's about 25 times more massive than Sagittarius A star, the supermassive black hole sitting at the center of our own Milky Way. This cosmic behemoth warps space and time around itself so severely that nothing, not even light, can escape once it crosses the point of no return, called the event horizon. Now here's something that should make you pause. We're seeing Andromeda's black hole as it was 2.5 million years ago. Whatever is happening there right now at this very instant, we won't know about for another 2.5 million years. The black hole could be actively feeding, tearing apart stars that wandered too close, generating brilliant jets of radiation that blast outward at nearly the speed of light. Or it could be quietly dormant, waiting in the darkness. We simply can't know. The information is still on its way. This brings us to one of the most profound implications of cosmic distances. We never see the universe as it is now. We only ever see the past. When you look at the moon, you see it as it was 1.3 seconds ago. The sun appears as it was 8 minutes and 20 seconds ago. The nearest star beyond our sun, Proxima Centauri, shows us its light from 4.2 years in the past. And Andromeda, we're looking back 2.5 million years every single time we observe it. Astronomers call this Lookback Time, and it's both a challenge and an extraordinary gift. It's a challenge because we can never observe the current state of distant objects, but it's a gift because it turns our telescopes into time machines. When we observe distant galaxies billions of light years away, we're literally seeing ancient light, watching how the universe looked when it was young. We can observe galaxies forming, stars being born, the cosmic web of matter taking shape. The farther out we look, the farther back in time we see. But here's something even more mind-bending about the distance to Andromeda. Space itself is involved in ways that challenge our everyday understanding of reality. You might think that if Andromeda is 2.5 million light-years away and light travels at a constant speed, then the light we see simply traveled in a straight line for 2.5 million years. But that's not quite right. During those 2.5 million years, the fabric of space itself has been expanding. This expansion is subtle over such relatively short cosmic distances, but it's still there, a reminder that space isn't just an empty stage where events unfold. Space is dynamic, stretching, evolving. Actually, this connects beautifully to another question. Why does the universe make it so difficult for civilizations to ever meet? I explored this exact topic in another video on this channel called Why the Universe Makes It Impossible for Any Two Civilizations to Ever Meet. The cosmic speed limit combined with these vast distances creates profound isolation. If you're curious about how this affects our search for alien life and why the universe might be teeming with civilizations that can never communicate, I highly recommend checking that out. The link is in the description and on the card above. Let's imagine for a moment that there's a civilization in Andromeda right now, 2.5 million light-years away. Perhaps they're astronomers studying the cosmos, just like we do. Perhaps they've built their own telescopes and turned them toward the Milky Way. What would they see? They'd be looking at our galaxy as it existed 2.5 million years ago, long before modern humans walked the Earth. They'd see no evidence of our cities, our radio signals, our presence. From their perspective, Earth would just be another anonymous planet orbiting an ordinary star in an ordinary spiral arm. Now imagine they decided to send us a message. Maybe they beam a powerful radio signal in our direction, carrying greetings, mathematics, music, anything to say, "We're here." That signal, traveling at the speed of light, would take 2.5 million years to reach us. If we received it tomorrow, we'd be seeing a message from a civilization as it existed 2.5 million years ago. They might not even exist anymore. Their entire civilization could have risen, flourished, and vanished into extinction, and we'd be reading a postcard from their ancient past. And if we wanted to respond, our reply would take another 2.5 million years to get back to them. The total round-trip communication time would be 5 million years. To put that in perspective, 5 million years ago, our ancestors were small primates in Africa who had just recently diverged from the ancestors of modern chimpanzees. Imagine trying to have a conversation where each exchange takes 5 million years. It's not a conversation at all. It's more like throwing messages in bottles into an ocean of time. This is the tyranny of distance in the cosmos. It's not just that things are far away, it's that the distances are so vast they create fundamental barriers to interaction, communication, and connection. The universe has built-in isolation, a cosmic loneliness enforced by the laws of physics themselves. Yet despite this, or perhaps because of it, there's something profoundly moving about our connection to Andromeda. Every atom in your body was forged inside stars. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was created in the nuclear furnaces of stars that lived and died billions of years ago. When those ancient stars exploded as supernovae, they scattered these elements into space, seeding the clouds of gas and dust that eventually collapsed to form new stars and planets, including our Sun and Earth. In a very real sense, you are made of stardust. And so is everything in Andromeda. The same physics that governs atoms in your body governs atoms in Andromeda. The same forces, the same particles, the same fundamental rules apply across the entire universe. When scientists study Andromeda's spectrum, analyzing the light from its stars, they see the same elements we find on Earth: hydrogen, helium, carbon, oxygen, nitrogen, iron. The universe speaks a common language written in the periodic table of elements. We are not separate from Andromeda. We are part of the same cosmic story, the same grand narrative of matter and energy evolving over cosmic time. And here's something that gives me chills every time I think about it. Right now, as you watch this video, photons of light are leaving Andromeda and beginning their 2.5 million year journey toward Earth. They won't arrive during our lifetimes, or our children's lifetimes, or for thousands upon thousands of generations, but they're coming. And when they finally arrive, if there are humans or whatever we've evolved into still looking up at the night sky, those distant descendants will see Andromeda as it appears right now, in this moment. We are connected across time and space in ways that transcend our brief individual existence. The distance to Andromeda also teaches us something crucial about the nature of scientific knowledge. For centuries, humans had no idea how far away anything in the night sky really was. The stars could have been holes poked in a celestial dome, or tiny lights just beyond the moon, or something else entirely. It wasn't until the early 20th century that we finally understood that those fuzzy nebulae visible through telescopes were actually entire galaxies like our own, scattered across incomprehensible distances. In 1923, astronomer Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory in California, made one of the most important discoveries in the history of astronomy. He identified Cepheid variable stars in what was then called the Andromeda Nebula. By measuring their pulsation periods and calculating their distances, Hubble proved beyond doubt that Andromeda was far outside our own Milky Way. It wasn't a nebula at all, it was an entirely separate galaxy. In one stroke, the known universe expanded from a single galaxy to countless billions. Our cosmic perspective shifted forever. Think about what that means for human understanding. Less than 100 years ago, we thought the Milky Way was the entire universe. Everything we could see, we believed, existed within our single galaxy. The idea of other galaxies, other island universes floating in the vast darkness hadn't yet taken root in our collective imagination. Hubble's discovery revealed that we lived in a universe far larger, far more magnificent, and far more humbling than anyone had dared to imagine. And we're still making discoveries that reshape our understanding. In 2026, the James Webb Space Telescope continues to revolutionize our view of the cosmos. Launched on December 25, 2021, this remarkable instrument orbits the Sun at a point called L2, roughly 1 million miles from Earth. Webb observes the universe in infrared light, allowing it to peer through cosmic dust and see objects too distant and too faint for any previous telescope. It's studying the earliest galaxies that formed after the Big Bang, analyzing the atmospheres of exoplanets, and revealing details about galaxies like Andromeda that we've never seen before. Webb has given us unprecedented views of Andromeda's structure, revealing intricate details in its spiral arms, dust lanes, and star-forming regions. We can now map the distribution of different stellar populations across the galaxy, identifying where new stars are being born and where older stars have settled into quiet old age. We can study the chemical composition of gas clouds, tracking the elements that will someday form new solar systems. Every observation adds another piece to the puzzle of how galaxies form, evolve, and interact over billions of years. But even with our most sophisticated instruments, we're still just scratching the surface. Consider this. Andromeda contains roughly 1 trillion stars, and we've only studied a tiny fraction of them individually. Each star is a unique world with its own story. Some are massive blue giants burning through their fuel at prodigious rates, destined to explode as supernovae in just a few million years. Others are small red dwarfs that will burn steadily for trillions of years, outliving the current age of the universe many times over. There are binary star systems, triple star systems, stars with planets, stars being born in stellar nurseries, and stars breathing their last breaths as they shed their outer layers into space. And the planets. Oh, the planets. We have no way to directly observe planets around individual stars in Andromeda. The distance is simply too great. But based on what we've learned from studying our own Milky Way, we can make educated estimates. Astronomers now believe that planets are common, perhaps universal. Most stars probably have planets. If that holds true in Andromeda, and there's no reason to think it wouldn't, then Andromeda likely hosts trillions of planets. Trillions. Rocky worlds like Earth, gas giants like Jupiter, frozen ice worlds in the outer reaches of their solar systems. Worlds orbiting binary stars experiencing double sunsets. Rogue planets ejected from their home systems, wandering the darkness between stars. Some of those planets almost certainly harbor life. The universe is simply too vast, the number of potential habitats too numerous for Earth to be the only living world. Perhaps there are microbes in the oceans of an icy moon. Perhaps there are jungles teeming with exotic organisms we can't even imagine. Perhaps there are civilizations, societies with their own art, science, philosophy, and dreams. Perhaps some of them are looking back at us right now, seeing the Milky Way as a faint smudge in their night sky, wondering the same questions we're wondering. But we'll likely never know. The distance separating us is too vast. Even if we detected a radio signal from Andromeda tomorrow, even if we confirmed without any doubt that intelligent life exists there, the communication gap would make meaningful exchange impossible. By the time our message reached them and their reply came back, 5 million years would have passed. Civilizations rise and fall in less time than that. The very concept of such a delayed conversation challenges everything we understand about communication and connection. This is where the distance to Andromeda becomes not just a scientific fact, but a philosophical meditation. What does it mean to know that something exists but to be forever unable to reach it? What does it tell us about our place in the cosmos that we can see so much but touch so little? These aren't just abstract questions. They cut to the heart of what it means to be human, conscious beings aware of our profound isolation in space and time. Yet I find something beautiful in this isolation. The fact that we're separated from Andromeda by such vast gulfs of space doesn't diminish our connection to it. If anything, it deepens the wonder. Every photon of light that completes that 2.5 million year journey is a miracle of sorts, a tiny messenger carrying information across the void. When we capture that light with our telescopes and decode its secrets, learning about the composition of distant stars, the motion of gas clouds, the structure of spiral arms, we're participating in something profound. We're reaching across the cosmos with nothing but curiosity and mathematics and the patient accumulation of knowledge. The ancient Greeks looked up at the night sky and saw myths. They connected stars into constellations, weaving stories about gods and heroes. The Babylonians tracked the movements of planets, developing early astronomy to predict eclipses and mark the passage of seasons. Medieval Islamic scholars preserved and expanded astronomical knowledge, cataloguing stars and refining instruments. Renaissance astronomers like Copernicus and Galileo challenged Earth-centered models of the cosmos, beginning the revolution that would eventually reveal our true place in the universe. Each generation built upon the work of those who came before, slowly, painstakingly expanding the boundaries of human knowledge. And now here we are, in the 21st century, able to measure the distance to Andromeda with precision, understand its structure, predict its future, and recognize it as a galaxy much like our own. We've come so far, and yet we've barely begun. There's a concept in astronomy called cosmic humility, the recognition that despite all our knowledge, we're still tiny beings on a small planet, orbiting an ordinary star in the outer reaches of an average galaxy. Everything we've ever known, every human who has ever lived, every civilization that has risen and fallen, all of it happened on this one pale blue dot suspended in a sunbeam, as Carl Sagan so eloquently put it. From Andromeda's perspective, if anyone there is looking, Earth doesn't even register as a pixel. We're invisible, insignificant, lost in the glare of our sun. But here's the thing. Insignificance doesn't mean meaninglessness. The fact that we're small doesn't diminish the importance of our questions, our curiosity, our drive to understand. In fact, it makes it more remarkable. Against all odds, on this one small world, the universe became conscious of itself. Matter arranged itself into patterns complex enough to think, to wonder, to build telescopes and equations and explore its own origins. We are the universe examining itself, asking where it came from and where it's going. And that brings us back to Andromeda. When we study that distant galaxy, we're not just learning about an object 2.5 million light-years away, we're learning about ourselves. Galaxies like Andromeda and the Milky Way formed from the same cosmic ingredients, following the same laws of physics. By understanding how Andromeda evolved, we understand our own galactic home better. By predicting the possible collision billions of years in the future, we're thinking about cosmic timescales that dwarf human history. We're placing ourselves within the grand narrative of the universe itself. Let's talk about what actually happens during a galactic collision, because the word collision is somewhat misleading. When we say Andromeda and the Milky Way might collide, you might picture two solid objects smashing into each other like cars in a crash. But galaxies aren't solid. They're mostly empty space. The distance between stars within a galaxy is enormous compared to the size of the stars themselves. If the Sun were the size of a basketball, the nearest star would be about 6,000 miles away. That's the scale we're dealing with. So when two galaxies merge, the stars themselves almost never actually collide. Instead, they pass by each other like two swarms of bees flying through one another. The real action happens gravitationally. As the galaxies interpenetrate, their gravitational fields interact in complex ways. Stars get flung onto new orbits. Some are ejected entirely, thrown out into intergalactic space to wander alone forever. Others are pulled inward toward the center of the newly forming galaxy. The elegant spiral structures of both galaxies get disrupted, torn apart by tidal forces. Gas clouds that were peacefully drifting through space suddenly get compressed, triggering massive bursts of star formation. Millions of new stars are born in a cosmic fireworks display that can last for hundreds of millions of years. Computer simulations of the Milky Way-Andromeda merger paint a spectacular picture. The two galaxies would first make a close pass, reaching their closest approach in roughly 4 billion years. At that point, assuming the collision does occur, Andromeda would dominate our night sky, stretching across a vast portion of the heavens. It wouldn't be a subtle, fuzzy patch anymore. It would be brilliant, obvious, magnificent, a river of stars and glowing gas clouds visible even in daylight. Of course, by then, our Sun will have evolved into a red giant, possibly engulfing Earth entirely, so there might not be anyone around to appreciate the view. After the first pass, the two galaxies would swing apart, their mutual gravity acting like a cosmic slingshot. But that gravity would eventually pull them back together for a second pass, then a third. Each encounter would further disrupt both galaxies, scattering stars, compressing gas, and redistributing matter. Eventually, after perhaps 1 billion years of this cosmic dance, the two galaxies would settle down into a single, massive, elliptical galaxy. The spiral arms would be gone, replaced by a more or less spherical or football-shaped distribution of stars. This new galaxy, sometimes nicknamed Andromeda, would contain roughly 2 trillion stars, making it one of the largest galaxies in our local cosmic neighborhood. But here's where the story gets even more interesting. Remember those supermassive black holes I mentioned earlier? Andromeda has one weighing about 100 million solar masses. The Milky Way has Sagittarius A star weighing roughly 4 million solar masses. When the galaxies merge, these two black holes would eventually sink toward the center of the new combined galaxy. And then something extraordinary would happen. They'd begin orbiting each other, gradually spiraling inward as they emit gravitational waves, ripples in the fabric of space-time itself. Gravitational waves are one of the most remarkable predictions of Einstein's general theory of relativity, published in 1915. For decades, they remained purely theoretical. But in 2015, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, detected gravitational waves for the first time, confirming Einstein's century-old prediction. The waves LIGO detected came from 2 stellar mass black holes, each weighing tens of solar masses, merging together about 1.3 billion light-years away. The detection opened an entirely new window on the universe, allowing us to observe cosmic events that don't produce any light at all. When Andromeda's black hole and the Milky Way's black hole finally merge, billions of years from now, they'll produce gravitational waves far more powerful than anything LIGO has detected. These waves will ripple outward through space-time at the speed of light, carrying away energy and angular momentum. In the final moments before merger, the two black holes will orbit each other thousands of times per second, whirling around at a significant fraction of light speed. Then they'll plunge together, combining into a single, larger black hole weighing roughly 104 million times the mass of our Sun. The energy released in that final merger, emitted purely as gravitational waves, would briefly outshine all the stars in the observable universe combined, though you wouldn't see it with your eyes. You'd need gravitational wave detectors to observe it. By the time this happens, if there are any civilizations in the merged galaxy, if there are any descendants of humanity still around, they'd have gravitational wave astronomy far more sophisticated than ours. They'd be able to watch this merger in exquisite detail, extracting information about the masses, spins, and orbits of the black holes with incredible precision. They'd witness one of nature's most violent and energetic events, all unfolding silently, invisibly, detectable only through the warping of space-time itself. Now let's zoom back out and think about Andromeda's place in the larger cosmic structure. Andromeda isn't alone in the universe, it's part of what astronomers call the local group, a collection of more than 100 galaxies bound together by gravity. Most of these galaxies are small dwarf galaxies containing anywhere from a few million to a few billion stars. The Milky Way has dozens of these dwarf satellite galaxies orbiting it, including the Large Magellanic Cloud and Small Magellanic Cloud, both visible from the southern hemisphere as fuzzy patches in the night sky. Andromeda has its own retinue of satellite galaxies, including M32 and M110, both visible through amateur telescopes. Just this year, in April 2026, astronomers announced the discovery of yet another dwarf satellite galaxy orbiting Andromeda. They named it Andromeda 36, also called Andromeda X in Roman numerals. It's what's called an ultra-faint dwarf galaxy, one of the least luminous, most dark matter-dominated galaxies known. These tiny galaxies are incredibly difficult to find because they emit so little light, but they're scientifically precious because they're thought to be fossils from the early universe, preserving information about how the first galaxies formed. The discovery came from analyzing data from the Pan-Andromeda Archaeological Survey, abbreviated as PANDAS, a project that systematically mapped the outer regions of Andromeda and its satellites. An amateur astronomer named Giuseppe Donatiello first spotted the overdensity of stars that turned out to be Andromeda 36. This is one of the beautiful things about modern astronomy. Professional researchers collaborate with dedicated amateurs, and together they push the boundaries of knowledge. You don't need a billion-dollar space telescope to contribute to science. You need curiosity, patience, and careful attention to detail. These dwarf galaxies tell us something profound about the nature of the universe. Most of the matter in galaxies isn't the normal atomic matter that makes up stars, planets, and us. It's dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. We only know it exists because of its gravitational effects. Dark matter holds galaxies together, keeps stars orbiting faster than they should based on visible matter alone, and provides the gravitational scaffolding that allowed galaxies to form in the first place. Ultra-faint dwarf galaxies like Andromeda 36 are dominated by dark matter. They might contain 99% dark matter and only 1% normal matter. By studying these galaxies, astronomers can probe the properties of dark matter itself. How is it distributed? How does it interact, if at all, beyond gravity? Does it decay or annihilate? These are some of the biggest unsolved mysteries in physics, and galaxies orbiting Andromeda might hold crucial clues. The local group itself is part of an even larger structure called the Virgo supercluster, or more recently renamed the Laniakea supercluster. This is a collection of roughly 100,000 galaxies spanning 500 million light-years. We're located on the outer edges of this supercluster, in what you might call the cosmic suburbs. At the center lies the Virgo cluster, a massive concentration of galaxies located about 54 million light-years away. The combined gravity of all those galaxies pulls on the local group, and we're slowly, imperceptibly, falling toward it at about 400 kilometers per second. But even that's not the end of the structure. Superclusters are arranged into filaments and walls separated by vast cosmic voids, nearly empty regions of space containing very few galaxies. If you could zoom out far enough to see the entire observable universe, you'd see a cosmic web, a magnificent foam-like structure with galaxies concentrated along filaments surrounding giant voids. It's breathtakingly beautiful, and it tells us about the initial conditions of the Big Bang, the tiny quantum fluctuations in the early universe that eventually grew into the large-scale structure we see today. Andromeda sits within this cosmic web just as we do, both of us embedded in a structure that stretches across the entire observable universe. And here's something that should make you pause. The observable universe has a boundary. Not because there's an edge to space, but because light has only had a finite amount of time to reach us since the Big Bang. The universe is approximately 13.8 billion years old, which means we can only see objects whose light has had 13.8 billion years or less to travel to us. Beyond that distance, the expansion of space carries galaxies away from us faster than their light can reach us. Those regions are forever beyond our view, invisible not because of technological limitations, but because of the fundamental structure of space-time itself. The edge of the observable universe sits roughly 46.5 billion light-years away in every direction. Wait, you might ask, if the universe is only 13.8 billion years old, how can we see objects 46.5 billion light-years away? Shouldn't the most distant objects be 13.8 billion light-years away? This is where the expansion of space creates something wonderfully strange. When light left those distant galaxies 13.8 billion years ago, they were much closer to us. But during the time that light has been traveling toward us, space itself has been stretching, carrying those galaxies farther and farther away. So by the time the light reaches us, the galaxy that emitted it is now 46.5 billion light-years distant. We see where it was, not where it is now. Compared to these mind-bending cosmic scales, Andromeda is right next door. 2.5 million light-years is nothing, a trivial distance, barely worth mentioning. The most distant galaxy ever observed as of 2026 has a redshift indicating we're seeing it as it appeared when the universe was only a few hundred million years old. That galaxy is now more than 30 billion light-years away. Compared to that, Andromeda is practically in our backyard. And yet, even being in our backyard, we can't reach it. We can't even send a spacecraft to the nearest star beyond our Sun, Proxima Centauri, a mere 4.2 light-years away. Our fastest spacecraft, Voyager 1, launched in 1977 and is currently traveling at about 38,000 miles per hour relative to the Sun. At that speed, it would take roughly 73,000 years to reach Proxima Centauri if it were heading in that direction, which it isn't. To reach Andromeda would take more than 44 billion years, far longer than the current age of the universe. This is the cruel mathematics of interstellar and intergalactic travel. The distances are simply too vast for chemical rockets or even nuclear propulsion. Some scientists have proposed more exotic concepts: light sails pushed by powerful lasers, antimatter rockets, generation ships where multiple generations live and die during the journey, or even more speculative ideas like warp drives that somehow contract space in front of a ship and expand it behind. These remain firmly in the realm of science fiction, at least for now. The physics might allow for them in principle, but the engineering challenges are staggering, perhaps insurmountable. But let's engage in a thought experiment. Suppose we somehow develop technology allowing us to travel at 99% the speed of light. Special relativity tells us that time would slow down for the travelers due to time dilation. From the perspective of someone on the ship, the journey to Andromeda might only take about 350,000 years of subjective time, rather than the full 2.5 million years that would pass on Earth. Still an impossibly long voyage, but significantly shorter for the travelers. Now suppose we push even closer to light speed, say 99.9999% of light speed. Time dilation becomes more extreme. From the traveler's perspective, the journey might be compressed to just a few hundred years, maybe even less, depending on exactly how close to light speed you're going. You could potentially have a generation ship make the crossing within a handful of human lifetimes. But here's the catch: while only a few hundred years pass on the ship, the full 2.5 million years still pass on Earth. Anyone you left behind would be gone, along with everyone they ever knew, and everyone those people ever knew for thousands of generations. You'd return to an Earth utterly transformed, unrecognizable, assuming humanity, or whatever we'd evolved into, still existed at all. This is the profound loneliness built into the structure of the universe. The speed of light isn't just a speed limit for objects. It's a fundamental constraint on causality, on communication, on connection itself. Einstein showed us that space and time are woven together into a single fabric called space-time, and that nothing with mass can ever reach light speed, let alone exceed it. You can get arbitrarily close, but the closer you get, the more energy it requires, approaching infinite energy as you approach light speed. It's a barrier written into the laws of physics themselves. Some people find this depressing. The universe is vast, possibly infinite, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, and we're trapped here, unable to explore more than the tiniest fraction of it. But I find it beautiful in a strange way. It means that right here, right now, on this one planet, we have something precious. We have each other. We can communicate, touch, share ideas, build civilizations together. The very isolation that seems so limiting is what makes our connections meaningful, and we can still explore in other ways. Every time we build a more powerful telescope, we're expanding the boundaries of what we can observe. The James Webb Space Telescope is just the beginning. Future space telescopes are already being planned. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will study dark energy and exoplanets. The European Space Agency is developing the Extremely Large Telescope, a ground-based instrument with a primary mirror 39 meters across, which will revolutionize our understanding of everything from exoplanet atmospheres to the formation of the first stars. China is planning space-based observatories. Private companies are entering the field. We're living through a golden age of astronomy, and it's only accelerating. Each new instrument reveals details about Andromeda that previous generations couldn't have imagined. We can now map the motions of individual star clusters within the galaxy, tracking how they orbit Andromeda's center. We can identify and study globular clusters, ancient spherical collections of stars that formed when the galaxy was young. We can observe stellar nurseries where new stars are being born, seeing the process unfold in real time, or at least in 2.5 million years delayed time. We can detect and characterize supernovae, the explosive deaths of massive stars, watching how they enrich the galaxy with heavy elements. In fact, supernovae play a crucial role in cosmic evolution. When massive stars exhaust their nuclear fuel, they can no longer support themselves against gravity. The core collapses in a fraction of a second, then rebounds in a catastrophic explosion that can briefly outshine an entire galaxy. In that explosion, elements heavier than iron are forged, including gold, platinum, uranium, and all the other heavy elements on the periodic table. These elements get scattered into space, mixing with gas clouds, eventually becoming incorporated into new stars and planets. Every gold ring, every silver coin, every bit of uranium in Earth's crust was created in a supernova explosion billions of years ago, probably before our solar system even formed. The atoms that make up your body have journeyed through multiple cycles of stellar birth and death. You are not just made of stardust, you are made of supernova dust, the ashes of dead stars. And the same is true for everything in Andromeda. The connection between us isn't just poetic. It's literal, written in the atoms themselves. This brings us to one of the most profound questions in cosmology. Why does the universe have the structure it does? Why do we see galaxies organized into groups, clusters, and superclusters? Why not just a uniform distribution of matter throughout space? The answer takes us back to the beginning, to the Big Bang itself and the first moments of cosmic history. Roughly 13.8 billion years ago, the universe began in an incredibly hot, dense state. We call this moment the Big Bang, though that's somewhat of a misnomer because it wasn't an explosion in space. It was an expansion of space itself. In the earliest fractions of a second, the universe underwent a period of exponential expansion called cosmic inflation, growing from subatomic scales to macroscopic size faster than you can blink. This inflationary period smoothed out the universe, making it remarkably uniform but not perfectly uniform. Quantum fluctuations, tiny random variations in the density of matter and energy, were stretched to cosmic scales by inflation. Those tiny fluctuations, differences in density of less than 1 part in 100,000, became the seeds of all cosmic structure. Regions that were slightly denser than average had slightly stronger gravity. They pulled in more matter from their surroundings, becoming denser still. Over millions and billions of years, this process continued, with denser regions collapsing under their own gravity, while less dense regions became increasingly empty. Eventually, the dense regions formed the first stars, the first galaxies, and eventually the cosmic web of structure we see today. We can actually observe these primordial fluctuations. The cosmic microwave background, abbreviated as CMB, is the afterglow of the Big Bang, radiation that has been traveling through space for 13.8 billion years. It fills the entire universe, coming at us from every direction. When we observe it with sensitive instruments, we see tiny temperature variations, hotter and cooler spots that correspond to those density fluctuations from the early universe. These observations, made by satellites like the Cosmic Background Explorer launched in 1989, the Wilkinson Microwave Anisotropy Probe launched in 2001, and most recently the Planck satellite launched in 2009, have revolutionized our understanding of the universe's origin and evolution. The CMB tells us the universe's age, its composition, the rate of expansion, and confirms predictions of the Big Bang theory with astonishing precision. It's one of the most important pieces of evidence supporting our current cosmological model, and those tiny fluctuations we see in the CMB, they're directly connected to the large-scale structure we observe today. The seeds that became galaxy clusters were already present when the universe was just 380,000 years old, encoded in the pattern of hot and cold spots in the ancient radiation. Andromeda itself formed from one of those overdense regions. Sometime in the first few 100 million years after the Big Bang, gas clouds began collapsing under their own gravity. The first stars formed, massive blue giants that lived fast and died young in spectacular supernova explosions. These early stars had no heavy elements, only hydrogen, helium, and traces of lithium created in the Big Bang itself. But their deaths enriched the surrounding gas with heavier elements, allowing the next generation of stars to form planets and potentially harbor life. Over billions of years, small proto-galaxies merged together, building larger and larger structures. Andromeda grew through a process called hierarchical assembly, smaller galaxies falling in and being absorbed, their stars becoming part of the growing whole. We can actually see evidence of this process when we study Andromeda in detail. The outer regions of the galaxy contain stellar streams, long trails of stars that were once part of smaller dwarf galaxies. These galaxies were torn apart by Andromeda's gravity as they spiraled inward, their stars scattered into these distinctive patterns that persist for billions of years. By studying these stellar streams, astronomers can reconstruct Andromeda's history, identifying when and where smaller galaxies merged with it. It's like cosmic archaeology, piecing together the past from the clues left behind. And the picture that emerges is one of continuous growth and evolution. Galaxies aren't static objects, they're dynamic, constantly changing, feeding on smaller galaxies, occasionally colliding with galaxies of comparable size. The merger between the Milky Way and Andromeda, billions of years in the future, is just the latest chapter in a story that's been unfolding for over 13 billion years. Now here's something that should blow your mind. We're learning all of this from light, photons of electromagnetic radiation traveling across 2.5 million light-years of space, carrying encoded information about their source. When we analyze starlight with a spectrograph, breaking it into its component wavelengths, we see dark lines at specific wavelengths where elements in the star's atmosphere have absorbed light. Each element produces a unique pattern of lines, like a fingerprint. By matching these patterns, we can determine what a star is made of, how hot it is, how fast it's moving, and much more. This technique, called spectroscopy, is one of the most powerful tools in astronomy. It allows us to determine the chemical composition of objects we can never physically touch. We know what Andromeda's stars are made of with the same certainty we know what our Sun is made of, even though Andromeda is millions of times farther away. We can measure the rotation speed of the galaxy by observing how light from stars on one side is redshifted, stretched to longer wavelengths because they're moving away from us, while light from stars on the other side is blue-shifted, compressed to shorter wavelengths because they're moving toward us. When we do this measurement for Andromeda, we discover something puzzling. The galaxy is rotating faster than it should based on the visible matter we can see. The outer regions especially are moving too fast. According to Newton's laws of gravity, stars farther from the galactic center should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. But in Andromeda, and in virtually every other galaxy we've studied, the rotation speed stays roughly constant even at large distances from the center. This is called the galaxy rotation problem, and it's one of the primary pieces of evidence for dark matter. The explanation is that galaxies are embedded in massive halos of dark matter, invisible material that extends far beyond the visible galaxy. This dark matter provides additional gravity, keeping the outer stars moving faster than they otherwise would. Current estimates suggest that about 85% of all matter in the universe is dark matter. Only 15% is the normal atomic matter that makes up stars, planets, and everything we can directly observe. We're living in a universe where most of the matter is completely invisible, detectable only through its gravitational influence. What is dark matter? Nobody knows for certain. It's one of the biggest unsolved mysteries in physics. It's not ordinary matter made of protons, neutrons, and electrons. We know that from multiple lines of evidence. It might be exotic subatomic particles that barely interact with normal matter, passing through us constantly without us noticing. It might be primordial black holes formed in the early universe. It might be something even stranger that we haven't thought of yet. Experiments around the world are searching for dark matter particles, trying to detect them directly. So far, we haven't succeeded, but the search continues. Understanding dark matter is crucial for understanding galaxies like Andromeda. The dark matter halo determines how the galaxy formed, how it evolved, how it interacts with neighboring galaxies. It's the invisible scaffolding that holds everything together. Without dark matter, galaxies as we know them couldn't exist. The universe would be a very different place, Probably one where stars and planets never formed, and we wouldn't be here to ask these questions. There's also dark energy, an even stranger component of the universe. While dark matter pulls things together through gravity, dark energy pushes things apart, driving the accelerating expansion of the universe. About 68% of the total energy density of the universe is dark energy. 27% is dark matter. Only about 5% is normal matter. We're surrounded by things we don't understand, living in a universe where 95% of the content is mysterious. Dark energy was discovered in 1998 through observations of distant supernovae. Astronomers were trying to measure the deceleration of the universe's expansion, expecting to find that gravity was gradually slowing it down. Instead, they found the opposite. The expansion is accelerating. Distant galaxies are moving away from us faster and faster as time goes on. This discovery was so unexpected, so contrary to everything physicists anticipated, that it took years of additional observations to confirm it. The astronomers who made this discovery, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics in 2011. What causes dark energy? Again, nobody knows. It might be a property of space itself, what Einstein called the cosmological constant. It might be a new type of energy field permeating all of space. It might be evidence that our theory of gravity needs modification on cosmic scales. Whatever it is, it has profound implications for the future of the universe. In the distant future, billions of years from now, dark energy will push galaxies apart so aggressively that most galaxies beyond our local group will be completely unreachable, not just in practice but in principle. They'll be receding from us faster than light can travel. This doesn't violate relativity because it's space itself expanding, not the galaxies moving through space. Eventually, if dark energy continues behaving as it does now, observers in the far future will see a lonely universe. Most galaxies will have disappeared beyond the cosmic horizon. Only the merged remnant of the Milky Way and Andromeda, along with a few other local group members, will remain visible. Those future astronomers, assuming anyone is still around, will have a very different view of the cosmos than we do. They won't be able to see the cosmic microwave background radiation because it will have been redshifted to such long wavelengths that it becomes effectively undetectable. They won't see distant galaxies fleeing in all directions. Their observable universe will consist essentially of their own galaxy floating in an otherwise empty void. If they try to reconstruct the history of the universe based solely on what they can observe, they'll have a much harder time than we do. Some of the crucial evidence for the Big Bang will have vanished beyond their horizon. This raises a fascinating question. What evidence has already disappeared beyond our horizon? What information about the universe's earliest moments has been lost forever because the regions of space containing that information are now receding from us faster than light? We're fortunate to live in an era when we can still observe the cosmic microwave background, still see billions of galaxies, still piece together the universe's history in a very real sense. We're living in a privileged moment in cosmic history for doing observational cosmology. But let's return to Andromeda and think about it in the context of this cosmic timeline. Right now, Andromeda is close enough that we're gravitationally bound. The local group, including the Milky Way and Andromeda, forms a small island of matter that will remain together even as the rest of the universe expands away. While distant galaxy clusters accelerate into the darkness, never to return, Andromeda is moving toward us. In 4 billion years, assuming current predictions hold, the merger will begin. By the time the universe is perhaps 20 billion years old, Andromeda will have formed, a single, massive elliptical galaxy in an increasingly empty cosmos. And what will happen to any planets, any potential life in these galaxies during the merger? The chances of any individual star being directly affected are actually quite low. Remember, stars almost never physically collide during galactic mergers because the distances between them are so vast. A planet orbiting a star in either galaxy would probably survive the merger intact, though it might find itself on a very different orbit around the new galactic center. However, there would be indirect effects. The merger will trigger intense bursts of star formation as gas clouds collide and compress. New massive stars will form, live brief lives, and explode as supernovae. The rate of supernovae in the merging galaxies will increase dramatically, perhaps by a factor of 10 or more. If you're living on a planet near one of these star-forming regions, you might witness supernova explosions with alarming frequency. A nearby supernova within a few tens of light years could be dangerous to life, bathing planets in harmful radiation and potentially triggering mass extinctions. There's also the disruption to planetary orbits from the changing gravitational potential of the galaxy. As the merger progresses and stars get redistributed, the gravitational field experienced by any given planetary system will change. Most planets would probably remain bound to their stars, but some might be perturbed into unstable orbits, eventually being ejected from their solar systems entirely to become rogue planets wandering through interstellar space. And what about our own solar system? Where will it end up in all this? Computer simulations suggest several possibilities. We might end up in the central regions of Andromeda, surrounded by billions of stars, experiencing a night sky far more spectacular than anything we see now. We might be flung outward into the outer reaches of the new galaxy, where stars are sparse and the night sky is darker and lonelier. Or we might be one of the unlucky systems ejected entirely, cast out into the intergalactic void, where we'd see no nearby stars at all, just the distant smudges of other galaxies impossibly far away. But all of this assumes the solar system still exists in recognizable form 4 billion years from now. That's far from certain. Our Sun is currently about 4.6 billion years old, roughly halfway through its main sequence lifetime. In another 5 billion years or so, it will exhaust the hydrogen fuel in its core and begin burning hydrogen in a shell around the core. This will cause the Sun to expand dramatically, becoming a red giant. The Sun's outer layers will extend outward, possibly reaching Earth's current orbit. Mercury will certainly be engulfed. Venus probably will be as well. Earth's fate is less certain. Some models suggest Earth will be consumed by the expanding Sun. Others suggest tidal interactions will cause Earth's orbit to migrate outward, allowing it to narrowly escape being engulfed. Even if Earth does survive as a physical object, it will be a scorched, lifeless cinder, all water boiled away, all atmosphere stripped, surface temperatures hot enough to melt rock. Life as we know it will be impossible on Earth long before the Sun reaches this red giant phase. In perhaps 1 billion years, increasing solar luminosity will trigger a runaway greenhouse effect, evaporating Earth's oceans and creating conditions similar to present-day Venus. Complex life will probably be impossible within a few 100 million years, so the galactic merger between the Milky Way and Andromeda, dramatic as it sounds, is actually not the most immediate threat to Earth's biosphere. The Sun's natural evolution will render Earth uninhabitable billions of years before the merger significantly affects our solar system. If humanity or our descendants hope to survive beyond the next billion years, we'll need to find new homes either elsewhere in our solar system, around other stars, or perhaps in artificial habitats in space. This leads to one of the great questions of our age. Are we alone? In all those trillions of stars in Andromeda and the Milky Way, across all those trillions of planets that probably exist, is Earth the only place where life has emerged? Is there intelligence elsewhere in the cosmos? This is the famous Fermi Paradox, named after physicist Enrico Fermi, who reportedly asked during a lunch conversation in 1950, Where is everybody? The paradox is this: the universe is vast and ancient. Even traveling at a small fraction of light speed, a technological civilization could colonize an entire galaxy in just a few million years, a blink of an eye on cosmic timescales. If intelligent life is common, we should see evidence of it everywhere: megastructures surrounding stars to capture their energy, probes visiting every solar system, radio signals filling the airwaves. Yet we see none of this. The universe appears silent, empty of obvious intelligence. Why? There are many proposed solutions to the Fermi Paradox. Maybe intelligence is extraordinarily rare, the result of an improbable chain of events that has only happened once in our galaxy, or maybe only a handful of times. Maybe intelligent civilizations inevitably destroy themselves before they can colonize their galaxy, falling victim to nuclear war, environmental collapse, or some other catastrophe. Maybe advanced civilizations deliberately stay quiet, avoiding drawing attention to themselves for reasons we don't understand. Maybe they're out there, but we're not looking in the right way. Or maybe the distances are simply too vast for meaningful communication. Or perhaps the most humbling possibility: maybe advanced civilizations exist, but they're so far beyond us, technologically and conceptually, that we can't even recognize their presence. Imagine trying to explain the internet to an ant. The ant crawls across fiber optic cables carrying terabytes of data every second, completely oblivious to the rivers of information flowing beneath its feet. Maybe we're the ants, crawling through a universe filled with intelligence and activity that we simply lack the capacity to perceive. The search for extraterrestrial intelligence, known as SETI, has been scanning the skies for radio signals from other civilizations since the 1960s. So far, we've found nothing conclusive. The famous WOW signal, detected in 1977, remains unexplained but has never repeated. Modern SETI efforts have expanded beyond radio waves to include optical signals, infrared searches for waste heat from advanced civilizations, and even searches for signs of massive engineering projects that might be detectable across interstellar distances. Andromeda has been included in some of these searches. If there's an advanced civilization in Andromeda trying to communicate with us, their signals would take 2.5 million years to reach us. Any message we detected would be ancient beyond comprehension, sent when our ancestors were primitive hominids just beginning to use stone tools. And if we replied, our response would take another 2.5 million years to arrive. Any conversation would span timescales longer than our entire species has existed. This temporal disconnect adds another layer to the isolation imposed by cosmic distances. Not only are we separated by vast gulfs of space, we're separated by vast gulfs of time. The Andromeda we see in our telescopes doesn't exist anymore, not in the form we're observing. Those stars have moved, some have died, new ones have been born. Any civilizations that existed 2.5 million years ago have either gone extinct or evolved into something unrecognizable. We're seeing a ghost, a fossil image preserved in light. Every deep space observation is a form of time travel, a window into the past. When we look at nearby stars a few dozen light years away, we're seeing them as they appeared within human historical timescales. When we look at distant galaxies billions of light years away, we're seeing them as they appeared when the universe was young, when our galaxy was just forming, long before the Sun and Earth existed. The universe is a time machine, and the farther we look, the further back we see. The James Webb Space Telescope is specifically designed to exploit this, to peer back to the earliest epochs of cosmic history and observe the first galaxies forming. Some of Webb's targets are so distant that we're seeing them as they appeared when the universe was only a few 100 million years old, less than 3% of its current age. These galaxies are incredibly faint, their light stretched to infrared wavelengths by the expansion of space, during its long journey to us. Webb's infrared sensitivity allows it to detect this ancient light, revealing galaxies that no previous telescope could see. When we compare these early galaxies to nearby galaxies like Andromeda, we can trace the evolution of galactic structure across cosmic time. We can see how galaxies have grown through mergers, how star formation has changed, how the chemical composition of the universe has evolved as successive generations of stars have enriched the cosmos with heavy elements. It's a story 13.8 billion years in the making, and we're only now beginning to read it. One of the surprising discoveries from Webb's early observations is that galaxies in the early universe appear more massive and structured than many models predicted. We're finding fully formed spiral and disk galaxies at times when the universe was supposedly too young for such structures to have developed. This might require revising our understanding of how quickly galaxies can form and grow, or it might reveal new physics about dark matter and the early universe. It's exactly the kind of unexpected result that drives science forward, forcing us to reconsider assumptions and develop better theories. Andromeda serves as a crucial benchmark for these studies. Because it's so close, we can study it in exquisite detail, resolving individual stars, star clusters, nebulae, and other structures. We can use this detailed understanding to calibrate our observations of more distant galaxies. When we see a fuzzy blob 10 billion light-years away, we can compare its properties to Andromeda's properties and make educated guesses about what that distant galaxy actually contains. Andromeda is our Rosetta Stone for understanding galaxies across the universe. The galaxy is also helping us understand stellar evolution. Different regions of Andromeda contain stars of different ages and compositions. The central bulge contains mostly old, red stars that formed billions of years ago. The spiral arms contain young, blue stars still forming from gas clouds. By studying these different populations, astronomers can piece together how stars form, evolve, and die. They can test theoretical models against real observations, refining our understanding of stellar physics. Globular clusters, those ancient spherical collections of stars orbiting Andromeda, are particularly valuable for this research. These clusters contain some of the oldest stars in the galaxy, formed when Andromeda was young. They're like fossil records preserving information about conditions in the early universe. By studying the chemical composition of stars in globular clusters, astronomers can determine what elements were present when those stars formed, providing clues about the supernova explosions and stellar processes that came before. Andromeda contains hundreds of globular clusters, more than the Milky Way's roughly 150. Some of these clusters are incredibly massive, containing millions of stars packed into spheres only a few hundred light-years across. If you lived on a planet in the core of one of these clusters, your night sky would be spectacular beyond imagination, filled with thousands of stars brighter than Venus appears from Earth. The combined light would be enough to read by, even at midnight. But planetary systems probably can't exist in the cores of globular clusters. The stars are packed so tightly that gravitational interactions would destabilize planetary orbits over time. Close encounters with other stars would be frequent on astronomical timescales, potentially ejecting planets from their solar systems. Life in a globular cluster core, if it exists anywhere, would face challenges we can barely imagine. Moving outward from the core, though, stars become more sparse, and stable planetary systems become possible. If life exists in a globular cluster, it's probably in the outer regions where stellar encounters are rare. And what stories those civilizations could tell if they exist? They'd be living in systems containing the oldest stars in the galaxy, stars that have been shining for over 12 billion years, watching the universe evolve around them. These ancient stars have witnessed cosmic history that we can only study indirectly. They were already ancient when our sun formed. They've orbited Andromeda's center hundreds of times, seen countless supernovae explode, watched as smaller galaxies merged with Andromeda and were torn apart. If we could somehow download the complete history recorded in the light from these stars, if we could see everything they've seen during their lifetimes, we'd have a direct observational record of half the universe's history. Of course, stars don't record and store information in any way we could access, but the metaphor is powerful. The universe preserves its own history in various forms, in the light still traveling through space from ancient events, in the chemical compositions of stars and gas clouds, in the large-scale structure of galaxies and galaxy clusters, in the cosmic microwave background radiation. We're learning to read these records, to extract information from them, to reconstruct the past from the clues that remain. If you made this far, make sure to give this video a like. And if you think Andromeda's distance is terrifying, wait until you discover the largest galaxy we've ever found. The video is on the screen. We're talking about a cosmic monster that makes Andromeda look tiny by comparison, a galaxy so impossibly massive it challenges everything we thought we knew about how large galaxies can grow. See you there.